In our first videotape on BBC Basic, we looked at the design of a program, breaking it down into procedures. And we looked at the input statement to get numbers into our program and print to print them out again. And we also looked at some graphics, some very simple line drawings. Now what we're going to go on and do during this videotape is to look in a little more detail at some of the facilities you can use within your programs. And we're going to start by looking at the different types of variable a program can contain: numeric variables and string variables. And you'll see the difference between them in this program. Now here we have a simple 6-line program, 3 input statements and 3 print statements. And we appear to be using the variable a in all cases. But there's an important difference. Here we have input and print for a by itself. Here, input and print for a%, and here for $1. Now these are 3 different variables, and they're 3 different types of variable. And we'll be able to see the difference as we try running this program. There's my prompt from the first input statement, asking me for a value of a. Let's use 100. A has been printed out, but instead of being printed right at the left-hand side of the screen, it's been printed out occupying a whole 10 characters. Let's try a%. Exactly the same thing has happened. The number 100 has come back, but it's been printed out in a 10-character field. $1, there's the first difference. When $1 was printed out, it wasn't pushed across towards the right. It was left at the left-hand side of the screen. The first difference between these variables is that a and a% are both numeric variables, and they'll hold numbers. $1 is a string variable, and it doesn't hold a number at all, but a string of characters. So although we typed in the 3 digits 100 for each of these 3 variables, when those digits went into a and a%, they were treated as a number. But in $1, they were treated as 3 separate characters. So our string $1 has been printed out without this extension to fill a field of size 10. Let's clear the screen and try it again with some different values. We'll list the program again so that we can keep an eye on which statement is being executed, and we'll run it again. This time we'll use the value 1.5, and we'll use 1.5 for each of our 3 variables. And there's the second difference that we notice. We put a value of 1.5 into a, and when we printed a, we got 1.5 back. Putting a value of 1.5 into a% and printing a% gives us 1. The 0.5 has been lost. $1 behaves as before. It doesn't treat 1.5 as a number, but as the 3 characters 1, 0, and 5. A% is an integer variable. This means that whatever value we try to put in it, it can only hold the integer part. It can't hold any decimal places. A, on the other hand, is a real variable, or you may see it referred to as a floating point variable. This means that it can hold not only the integer part of a number, but also any decimal places it may have. If we tried running the program again with a different set of numbers, let's use 1.12345. Again, the difference between a and a%, all those decimal places have been retained in the variable a, but we're still left with only the integer part in A%. Now, there are various things we need to look at with regard to the processing of numeric variables. And we'll start by looking at this business of having them printed out in a 10-character field, because often it's not convenient, if we're trying to fill our screen with numbers, to have them all occupying 10 characters. Well, we have another small program here, and we'll use that to experiment with printing numbers in different formats. Now, what we're doing here is inputting a value for our variable a, assigning that value to a second variable A%, and then printing them both out. The quotation mark I've put between A and A% in the print statement forces BASIC to print them onto separate lines. So if we run this coding and put in 1 as the value, then A and A% have both been printed in this 10-character field. Now we can change the size of this field by using a special variable that BASIC has. It's called @%. Let's see the effect on this program of assigning a value of 5 to @%. If we run it again using the value 1, you can see the difference. Instead of the ones appearing with a width of 10 characters, our ones have appeared with a width of 5 characters. So in the simplest way, we can change @% by giving it the value, which is the number of characters we want to have printed for numbers, and then any print statements we execute after that time will use that width. If we clear the screen, run the program again, let's try it with some long numbers. Here I've got 6 digits to be printed and a decimal point. There's the 5, because the integer value, A%, can still get into a 5-character field. But because A has more than that many digits, BASIC has decided that it can't print it within the constraints of 5 characters and has gone ahead and printed the whole thing anyway. Now, we've only seen one very simple use of @%, putting a simple number into it to change the width with which a number can be printed on the screen. But if you look in your user guide, you'll find that @% has several different parts, and by adjusting each of them, you can change other things about the way the number is printed. Well, we won't discuss them on the videotape, but when we record the program to show you these facilities, we'll include some examples of using @% to give you different results. And then you can look through that program in conjunction with your user guide to see the sort of effects that you can obtain. Now, we've looked at real variables and integer variables, and we haven't really come up with a good reason why one should use integer variables at all, because they can't hold any decimal places. So why don't we use real variables for everything? Well, one reason for this is speed. Integer variables are quite a lot faster than real ones, and I can demonstrate that with this program. Now, this coding has 3 repeat loops in it. Repeat until, repeat until, repeat until. In this first loop, we're going to time how long it takes to add 1 to a variable a 100 times. We start with a being 0, and we repeat until a is equal to 100, a equals a plus 1. And so we'll loop around this 100 times, with a getting bigger by 1 each time, until we've reached 100. Now, this statement, time equals 0, sets the computer's clock back to 0. Time is a function in BASIC, which we can use to access the clock. Here we're using it like a stopwatch. We're setting it to 0 at this point, and then here in this print statement, we're printing the value of time. So having set time to 0 before we do the loop and printing time afterwards will give us an idea of how long this loop took. Time goes up each 1/100th of a second. So the number printed out here will be the number of 1/100ths of a second it took to do this loop. So the first loop uses the variable a. The second loop is exactly the same coding, but using the variable AA%. The third loop does the same thing with A%. So A is going to be a real variable. Both AA% and A% are going to be integer variables. When you see the times, you'll see why I've included both of these. The tabs in the three print statements have simply requested that the times be printed on these lines so that we can see how they relate. Right, let's run the program. Well, it didn't take very long, and here are our three results. Remember, these are hundredths of a second. Our real variable a took 27 hundredths. That's just over a quarter of a second. Our integer variable AA% took 21, and A% took 16. So there's quite a big difference in speed between real and A%. Now, what's the difference between AA% and A%? They're both integer variables, but A% is rather special. You'll remember that we can use any series of letters we like for a variable name. But any integer variable whose name consists only of a single letter, followed by a percent, A%, B%, up to Z%, is one of a set of variables called the resident integer variables. Now they're special because they're faster and also because they're safe. Even if your program is destroyed, the values in those variables will be kept. I'm going to press break now. Now you wouldn't normally do this when you're running a program. We'll lose our blue screen, but we'll be able to see which of our variables have kept their values. Back to the initial BBC Computer basic screen. Let's print A. No such variable. Let's print AA%. Again, no such variable. If we print A%, we get 100. That's the value that was left in A% after we went round that loop, adding 1 to it. So real variables have the advantage that we can put any value into them, whether or not it has decimal places. But integer variables have the advantage of speed, they're quite a bit faster. And if we use the resident integer variables, that's the ones whose names consist only of a letter and a percent sign, then those values will remain safe, even if we go from one program to another. So they can be very useful when we have one program which wants to pass values to another program that's going to be executed immediately. Now, as we're talking about processing numbers and processing numeric variables, there are two more operations we should look at. They're called div and mod. And I have a little bit of coding here which will show you how they work. What I've done here is to put values, 8 and 5, into variables a and b, both of them real variables. And then these three print statements will print out the results of a divided by b, a div b, and a mod b. Now, divided by is the normal division, and it works in the way that we'd expect it to. Div is integer division. It takes the integer value of a, the integer value of b, divides a by b, and gives us the result as an integer. And related to that is mod, which gives us the remainder when we divide the integer value of a by that of b. Let's run the program and see what results we get. A divided by b is 8 divided by 5, which is 1.6, as we'd expect. A div b is the integer result of dividing 8 by 5. So it's effectively the integer value of 1.6 in this case. A mod b gives us the remainder 3, which is the remainder when we divide 8 by 5. Let's try that again, but with a different pair of values. I've changed this program slightly to use different values. I've used non-integer values for a and for b, 12.1 and 2.1. If we run this version of the program, you'll see something quite important, that although a divided by b gives us a value of 5 point several decimal places, a div b gives us 6, because both a and b are changed to integers before the division is done. So the 0.1 is ignored in each case, and a div b is effectively 12 divided by 2, giving us 6. Similarly, a mod b, the remainder, gives us nothing, because that's working in the same way, dividing 12 by 2 and giving no remainder. Well, we've looked at some different things we can do with numeric variables, some of the different operations and some of the advantages and disadvantages of each type. Now we're going to have a break at this point, and on the soundtrack of your video cassette you'll find a program which demonstrates the things we've been talking about. When we come back at the end of that program, we'll move on to look at string data and the things we can do with that. Now, although we use computers a lot to process numbers, we'll also find many times when we need to process strings of characters as our data. They could be people's names or addresses. It could be the high score table in the game you're writing. So we need variables and we need functions and different types of statements that will allow us to manipulate strings of characters. Well, I've got a very small program here which will start us off looking at some of those functions. If we run it, we'll get this, an invitation to enter my name. Well, I'll use my name. And it gives me back 2 numbers. Now the first of those numbers, the 14, is the total number of characters that I typed. And the second number, the 6, is telling me how far from the beginning of the string the first space was. So it's giving me information which will allow me to work out how long the first name was and how long the second name. Well, if we clear the screen and look at the listing of the program, we'll see the 4 statements that did that. Statement 10 is an input statement, inviting us to enter a name, giving a single quotation mark so that the value we type in will go on to the next line, and then accepting a value into the variable name $. And remember, because of the $sign at the end, it's going to be a string variable. The second line, 20, puts a value into gap percent. And the value that's going into gap percent is the value that this function, instra, will give us. Now Instra looks in one string to see if it can find another. The two strings we've used are name dollar, value we typed in, and a string containing just a single space, quotation marks at either end with a single space in between them. So Instra will look along the value of name dollar, searching for a space. As soon as it finds one, it'll stop looking, and the value it gives us back will be the position of that space. The next line, 30, puts the value into L%, using a different function, which is len, to give us the length of a string. The value len gives us back is the total number of characters there are in name dollar. So that when we print out L%, the length, and gap%, the position of the first blank in the name, we'll have those two pieces of information we saw a moment ago. Let's run it again using a different name. We'll try Joe Soap. We've typed in a total of 8 characters. Remember that space counts as a character. 3, 1, and another 4 gives us 8. The value of gap% is 4, because that space occurs in the 4th position in the string. Now, having got those two pieces of information, we can then go ahead and calculate how long the first name is and how long the second one. And I've got another version of this program which uses those two pieces of information in just that way. Well, we'll run the program first to see what it does. The same prompt, enter your name. And as you can see, the program has managed to split that into its two halves, giving us the first name and the second name. Well, I'll clear the screen and list the program for you so that you can see the statements that do that. The first 3 statements here are the same as the ones we saw before. These next two, lines 40 and 50, put values into first dollar and last dollar. And these are 2 new string variables that we're going to be using. We've used 2 new functions here as well, mid dollar and right dollar. Notice that these functions have dollars as part of their names, and this tells us that the value they give back is a string value and not a number. Instra and len both gave us back numbers, so their names did not contain dollar signs. Now mid dollar gives us the value of a part of a string. The first value we've specified is name dollar, the name we typed in. The second is a number, and this tells us where within this string we want to start. This number tells us how long we want the string to be. So we've said, using mid dollar, take the value that's in name dollar, that's this variable here, starting in position 1, and for length gap%. Gap%, remember, was the position of the first space. Take out a string from the middle and put that string into first dollar. Line 50 uses the function right dollar, and that's going to take characters from the right-hand end of name dollar. How many of them? Well, that's what the second value here specifies. L% minus gap%. Well, L% is the total number of characters. Gap% is the position of that space character. So right dollar should give us all the characters after the space and put them into last dollar. And finally, our 2 print statements print out first dollar and last dollar. We'll just run that program with Joe Soap. and see what numbers will have been involved. L% will be 8, a total of 8 characters. Gap percent will be 4, position of the first space. So into first dollar, we're putting the middle of the value of name dollar, starting in position 1, and of length gap percent, of length 4. So we'll take the first 4 characters of this name, J, O, E, and the space, and put them into first dollar. Into last dollar, we're taking characters from the right of name dollar. How many characters? L% is 8, gap percent is 4. That gives us a value of 4 characters from the right-hand end of name dollar. The last 4 characters of name dollar are soap. And so that's what we've had printed out as our second name. Let me just clear the screen, list the program, and run it again using a slightly different name. Instead of Joe space soap, I'm going to put several spaces in between the 2 words. And there's the result. The first name still looks all right, but all those extra spaces, or at least most of them, have appeared as part of the second name. And that's because of the way this statement worked. Gap percent found the position of the first space, and so into last dollar, we put all the characters following the first space. Because we had several spaces in between the words, our second name has spaces at the beginning of it. And there's one other small problem with this program, and that's to do with the value of first dollar. Here, into first dollar, we've put 4 characters, J-O-E and the space. Whereas in fact, really, we should only put 3 characters. That space isn't part of the first name. So we're going to need a slightly more complicated version of the program to do the job properly. If we run the program, we can check to see if it works. And I'll put several spaces in between the 2 names. And yes, we seem to have achieved the correct result. Instead of all those spaces having been carried forward to the beginning of the second name, only the last non-space characters have been put into the second name. Let's check that we've got the correct length for the first name, and I can do that by printing the length of first dollar. Its value is 5, which is the correct number of characters for the first name. Well, I'll clear the screen and list that coding so that we can see how we achieved that result. We've inserted an extra line of coding here, line 60. It's quite a complicated line, so we'll have to go through it slowly. Line 50 puts into last dollar all the characters from the right-hand end of the name, including maybe some extra spaces. Now the first statement here in line 60 checks the first character of the last name. If left dollar, last dollar, comma 1 is equal to a space. Left dollar is the opposite of right dollar. It looks at characters on the left of the string. We've taken 1 character from the left end of last dollar, and we're asking if it's a space. If it is a space, then we have to remove that space and any others following. But if the answer to that is no, that the last name does not begin with a space, then we can continue straight down here and print out the first and second names. So let's look at this coding, which is the work we do if we found a space. It's a repeat loop. repeat until. Repeat until left dollar, last dollar 1 is not equal to a space. So that's the opposite comparison to the one we made there. Less than and greater than together mean not equal to in BASIC. So we're going to execute this statement over and over again until there are no spaces at the beginning of last dollar. So what does this statement do? It puts into last dollar the value returned by mid dollar. You remember we've already used mid dollar to take a section of a string. We're doing it again here, but we've only put 2 values in brackets after it. Up here we used 3 separate values. We're going to take the middle of string last dollar, starting with a second character, and because we haven't put a third value there, it'll go all the way to the end of the string. So the effect of that statement is to put into last dollar the value it had, but without the first character. So we're removing spaces from the beginning of last dollar until there aren't any more spaces left at the beginning of last dollar. If we run the program using Joe Soap with 3 spaces in between, then gap percent will have been 4, L percent will have been 3 plus 3 plus 4, giving 10. First dollar will be the first 3 characters, because we've made that correction. We've reduced the length by 1. And last dollar will be all the characters in name dollar, starting at the right-hand side, of length 10 minus 4, 6. So we'll have the 4 letters for soap and the 2 spaces that are on the front of them. This will be true. The first character of last dollar will be a space, so we remove the space from the beginning of last dollar. This is not true, because we do still have a space at the beginning of last dollar, so we'll repeat again and remove another space from the beginning of last dollar. Having removed 2 spaces, we'll now be down to soap, just the 4 characters. That will be true. The first character of last dollar is not a space, and so we can continue and print out the 2 names. Now we've looked at some of the functions that BASIC provides you with for handling strings, and some of the ways in which you can use them. But there are quite a lot of them, and they do require careful attention. After you've watched this session of our videotape, I would recommend strongly that you check all those functions in your user guide. Look at all the rules for using them and the values they give you back. And experiment with them. Take the program that we've been working with and change it. Make it work with several different names. Make it remove spaces at the front of the first name if there are any. To help you do that, we've recorded that program onto the soundtrack of this video cassette, and that follows immediately. After that program, we'll start looking at some graphics. When we started using graphics, we used move and draw statements, and all the positions on the screen, positions to move to and positions to draw lines to, used absolute coordinates. That is, that they measured all distances from the origin, which is in the bottom left-hand corner of the screen. So that if we were writing a procedure to draw a house, then the coding would look something like this. I've written a procedure and I've called it proc house. And the purpose of this procedure is to execute all the move and draw statements necessary to produce a little house. We start by moving to 200, 200, which is fairly close to the bottom left of the screen. And all the numbers I've used in the move and draw statements refer to absolute coordinates on the screen. All the x coordinates are measured from the left-hand side. All the y coordinates are measured from the bottom. I can get this house drawn simply by entering proc house. And there you see it. A very simple line drawing. Now that's all very well, but if I wanted a house in a different place on the screen, then I'd have to go and change all of these numbers, because these are all absolute positions on the screen. If I want a more flexible technique for doing drawings, which will allow me to change the position very simply, then I can use another statement instead of move and draw, and that's the plot statement. If we imagine that this is part of our graphic screen, then this bottom left-hand corner is the origin, and its coordinates are 0, 0. And we can refer to any other point on the screen by using as its coordinates the distance up and along, measured from the origin. And these are called the absolute coordinates. So in the x direction, this point would have address 3, and in the y direction, it would have a coordinate of 6. So if we were going to draw a shape such as that using absolute coordinates, then we would have to find the coordinates of every point on that shape that we were going to draw lines to and put those coordinates in our program. That's how we do it with move and draw. But if we're going to use plot, we can use another technique. We can move to this point, and then instead of working out the absolute coordinates of the next point and then of the next one, we can say to get from this point to this point, we have to move no distance in the x direction, but we have to move 2 points in the y direction. Similarly, to get from this one to this one, we're moving 2 points in the x direction and 1 in the y direction. So the coordinates of that point relative to that one are simply the distance one has to move to get from one to the other. To get from here to here, although we have an x coordinate of 2 relative, we're coming down the screen, so we have a negative distance in the y direction. Now, by using a plot statement, we can compose a shape that forms a house or whatever else it is that we want to draw. We can then move to any point on the screen, and that can then be plotted in that position on the screen using relative coordinates. Let's look at the coding that does that. Now here's a second version of that procedure. I've called it proc house 2. And instead of move and draw, we've used nothing but plot statements. Plot 1 and plot 0. You'll notice that the plot statement has 3 numbers following it, compared with the 2 numbers we used for move and draw. This is because the first number tells BASIC what sort of plot we want. Plot 1 is a drawing plot, and plot 0 is a move without drawing. But the difference between plot 1 and draw is that these 2 numbers are relative coordinates. They're relative to the point where we are now. Similarly, plot 0 is a move relative to where we are now. So if we take this one as an example, no matter where we were on the screen, if we then executed this plot statement, which is a relative move without drawing, we'd move 0 positions in the x direction and 50 positions in the y direction, so that we'd move straight up 50 graphics units. Now don't worry too much about trying to remember all the numbers we've used here, because we'll record this coding on the cassette a little later. Now, the advantage of having a relative move and draw instructions here is that we can go to any point on the screen and then execute proc house 2, and our house will appear. Let's suppose we want one around here somewhere. Well, let's suppose that that was position 600, 500. We can start by moving to that position. We can't see anything because, of course, move doesn't change the screen at all. But if we now say proc house 2, we get a house. And it will have started in position 600, 500. If we want another house in a different place, suppose we want one somewhere up here on the screen, we can move to a different point and call the same procedure again. Let's move to 800, 800. Again, we can't see anything because we simply executed a move. And now, to save myself some effort, I'll use the copy key and call the same procedure again. As you can see, another house has appeared, but this time we started in position 800, 800. So, relative drawing and moving using plot 0 and plot 1 can be very useful if we want to move a shape from one position in the screen to another position. Having done the work of defining our shape, we can then use it as many times as we like on the screen, putting it in any position that the computer can reach. Now, if I didn't stop it, that program would continue forever. So I'll press escape and break out of it. Let's have a look at the coding that I used to call proc house over and over again to draw houses in different places on the screen. The first 6 lines of this program do the work, so let's have a look at them. First statement, mode 1, but if you're using a 16K machine, then of course you could have used mode 4. You've seen a VDU19 statement before. In this case, I wanted a blue background, so VDU19 0 for the background color to be changed to color number 4, which is blue. I now have a repeat loop, repeat until false. And false is a special value that BASIC gives us, which will never be true. And so this loop would continue forever until I stopped it some other way. I have a move statement, and I'm using 2 occurrences of a function called RND. This gives us a random number. I've said RND 1000, and so that's a random number between 1 and 1000. So the effect of this move statement is to move to a random position on the screen with an x coordinate, which is a random number from 1 to 1000, and a y coordinate, which will be a different random number between 1 and 1000. Let's just leave this statement for a moment. Just check. Here we have proc house 2, the statement which calls the procedure to draw the house. So move and draw the house. Move to a different position, draw the house again. So the house will be drawn starting in whatever position this move statement took us to. This statement here, I equals in key 15, is an easy way to slow the proceedings down. This causes a delay of 15/100ths of a second between the drawing of one house and the drawing of the next one. What the in key function actually does is to wait for up to that many hundredths of a second for a key to be pressed. If I'd pressed the key in that time, the key number would have been put into I and we'd have continued. As I didn't touch any keys, it caused a delay of 15/100ths of a second between the drawing of one house and the drawing of the next. If I remove that statement and repeat the program with just proc house 2 in that position, you'll see how much faster it goes. Now, it's all very well to do simple line drawings in one color, but with a computer like the BBC machine, we ought to be able to do something a little more adventurous, and of course we can. For a start, we can fill in solid shapes by making those shapes out of a series of triangles, because one of the plot codes tells the computer to draw and fill in a triangle. And of course we can change color while we're doing the drawing. Let's look at a different version of the program, which is doing basically the same thing, but including both of those facilities, a color change and a triangle fill. So here we have not a white outline of a roof, but a solid red roof, which is a single triangle. And if you look closely at the door, you'll see that that's a red rectangle, which in fact we've constructed out of two red triangles drawn side by side. Well, let's stop that and have a look at the coding that produced that. Here's the revised version of proc house 2. And the first thing we notice is these two gcol statements. Gcol stands for graphics color and is the statement we use to change the color in which graphics are drawn. It doesn't affect the text at all, only the graphics. The 3 and the 1 in these positions say logical color 3 and logical color 1. As I said, I'm using mode 1, so logical color 3 is white, logical color 1 is red, although I could change those using my VDU19 statement. If you were using a 16K machine, you could get the same effect in mode 5. Now the other differences come with these statements, the plot 81 statements. Plots can have various numbers from 0 up to 87. 81 says plot a triangle using relative coordinates and fill it in. This one does the roof, and these two together do the front door. Two triangles side by side which form a rectangle. Now when we use a plot 81 to draw a triangle, it uses the point that we specified in the plot statement and the last 2 points we visited. So in order to see exactly where this triangle would appear, we'd have to go back and work out where that point was and where that point was, because BASIC is going to join up these 3 points together to decide what triangle to fill in. Similarly, for this plot 81, it'll fill in a triangle defined by this point, and this one, and then the final plot 81, a triangle defined by these 3 points. Now we've only touched on a few of the numbers that you can specify with plot, but when you read your user guide, you'll find that there are a great range of plot codes going from 0 up to 87, all doing different things. And for each one that you read about, you need to check to see whether it uses relative or absolute coordinates, whether it's a move or a draw, whether it's drawing a line or filling in a triangle, or doing any of the other things that plot codes can do. However, it's worth experimenting with them. You can't do any harm, and you may very well produce some interesting effects. Now, we'll record this program, the one drawing the houses, onto the soundtrack of this video cassette, so that you can look at it and use it as a basis for your experimentation. That's one way of producing shapes on the screen, using draw, move, and plot statements. But there's another totally different way, which involves printing characters. Now, we could make shapes with the characters that are provided automatically by the machine, but we are allowed the facility to define our own character shapes. And we can use these to produce animals, men, whatever shape we want, as long as we can describe the character that has that shape. Now, all the characters displayed in modes 0 through to 6 on the machine are expressed in terms of an 8 by 8 square of dots. So the first thing to do when you want to design a character is to get yourself an empty chessboard. Now, in order to design one of our own characters, we have to imagine that each character occupies a square consisting of 64 spots, 64 points of light, 8 across and 8 down. And we design a character by imagining whichever ones we want filled in whatever color we're going to use. All the letters, except in mode 7. For example, an A would be designed as certain of these points of light turned on and certain turned off. Now, there are a large number of possible configurations of on and off. I'll give you an example of one I drew out a few moments ago. This would be a single character on the screen, as long as we can describe to BASIC exactly what points of light are switched on in each of these rows across. The way we do this is by writing a list of 8 numbers. Each of these numbers is a value for one of these rows of points. We have to think of the points in this row as being worth 1 each. In this row, 2, 4, 8, 16, 32, 64, and 128. And then for each point that we filled in, we have to add up the values for the whole row. Now, that sounds a little bit complicated when I describe it on a piece of paper. So I've written a program which we'll record on the soundtrack to help you design your own characters. So let's transfer this picture to the screen and see how it works. This area represents one character, and the program has drawn it as a large block so that we can easily see what it's going to look like. This column of numbers down the side gives the value of each of these rows of dots, 8 of them forming one character. At the moment, they're all set to background, so all these numbers are 0. These numbers here remind us of the value of each position along the row, from 1 on the right-hand side up to 128 on the left. And I've used these two symbols to show which pixel, which point of light we're pointing to. Now the program is written so that when I press the tab key, that block is changed in color. Its value is added into the appropriate figure on the right-hand side. And then down at the bottom here, we see how the character is progressing in 3 different colors. To turn a different point on, I use the cursor keys. To move to the right, if I press tab again, you can see I've got another point of color here. My character now consists of 2 spots, and the value for this row is 136. 128 for this spot and 8 for this one. So 136 followed by 7 zeros would describe a character looking like that, one with 2 spots. So our next job is to transfer this picture of our little man onto this grid. Well, we'll use the space bar to rub that one out because we don't need it, and then start filling in dots on the top row. Down to the next row, leave a space for his eyes, and the next row. That's the end of his left foot. Now you can see here that I've copied the shape of the complete figure onto my grid. I now have my 8 numbers down the right-hand side, which I will use to describe this shape. And here I have my 3 little men in 3 colors, showing me what it will look like when it's printed as a single character on the screen. If I now press return, these 8 numbers will be incorporated into a VDU statement, which I can copy down and use in one of my programs. So I'll press return. It's a VDU 23 statement. Check this in your user guide, because this is a statement used to define your own characters. There is the set of 8 numbers which describe that character. And where the program has printed 3 question marks is where we have to insert a character number. We can use characters from 224 up to 255 for our own purposes. So I'll use the editing keys and I'll copy that statement, only I'll make it character number 240. I've now executed that VDU statement saying that character number 240 is going to be defined by that series of numbers. And now I need to be able to print character 240. Well, there are 2 ways of doing that. One is to say print and then use the $CHR function, which stands for character, with the number in brackets after it. That says print the character whose number is 240. If I do that, you see I get my little man. The alternative is to use a VDU statement simply specifying the number, VDU 240. And we get the same result. We've described that character, it's now been stored within the machine's memory, and every time we print character number 240, we'll get this little man. Depending, of course, on how many of him I want, I could write a loop or write a program to print out hundreds of them. As I said, we'll record a copy of that program onto the soundtrack so that you can then use it yourself to define your own programs. Well, we've just about come to the end of this tape. We've looked at different types of number processing, We've looked at manipulation of strings. We've looked at using graphics and the plot statement, and we've done a little character definition. This should set you fairly well on the way to writing quite complicated programs, especially if you look at the coding we've provided and you follow things through by reading the appropriate section in your user guide. So, good luck with your programs, and I'll leave you with our little friend.